Hello, everyone. Thank you for watching this presentation. My name is Sayed Saad Afzal, and I am a PhD student and a research assistant in the Signal Kinetics group at MIT. Today, I'll be telling you about our research on battery-free underwater GPS. One of the most revolutionary technology of our time is GPS. It has opened up an enormous amount of applications ranging from navigation to location-based services, and it has really transformed our lives. Unfortunately, GPS does not work underwater, and the reason is that it uses radio signals which do not propagate well below the water surface. And in fact, today you have nothing like a global positioning system for underwater environments, and it's actually very challenging to build one. Now you may wonder why we want underwater GPS. Well, underwater GPS technologies are great in trust due to its potential for ocean exploration, scientific research, and commercial activities. By using this technology, robots can be deployed to any location in the ocean and navigate their way back to provide valuable information. The ocean is largely unobserved, with more than 80% of it still remaining unexplored, and underwater GPS can help us to map the seas and provide insights into this unknown territory. Batteryless underwater GPS also offers us valuable information on climate and weather patterns. Understanding the ocean's role in climate change is critical, but location-type data is lacking. Underwater GPS can provide us location information that can then be used to build more sophisticated models for understanding climate change. Another practical application for underwater GPS is studying marine animals. With this technology, we can locate, track, and study fish to better understand their life cycles and support endangered species. This knowledge is crucial for making aquaculture sustainable, which is one of the fastest growing food sectors of our time. Unfortunately, existing technologies have not yet provided a persistent and scalable platform for underwater localization. So underwater localization today is typically achieved using acoustic signals or sonar. So for example, if a drone needs to be localized underwater, it sends out a sound wave that travels through the water, and then this sound wave is then detected by a network of anchored sensors that are strategically placed in the water, and then the sensors respond back to the sound wave immediately, allowing the drone's location to be pinpointed with a high level of accuracy. And by measuring the time that it takes for this round-trip path, it can estimate the distance using the speed of sound. By knowing the distance from each of the anchored sensors, the drone can do trilateration and position itself. And this is great, except that there's one problem. And the problem is that acoustic signals are very power hungry. And if you use these sensors to continuously generate acoustic signals, they're going to run out of energy very fast. And this is why underwater positioning remains one of the largest research problems for oceanographic researchers. Today, I'll tell you how we can build a battery-less underwater GPS. So we propose to replace the sensors with a battery-free sensor. Now, when the underwater drone sends out the signal, the way these battery-less sensors work is that they first harvest energy from the received signal. And then once they have sufficient energy, they can start applying back to the drone. In this way, the sensor can completely operate battery-free. This approach is ultra-low power, scalable, and very cost-efficient. We can deploy a large number of these battery-free anchors underwater and then let them stay there forever, since we know that they will wake up once we need them. But clearly, there's an issue in this approach. The problem is that there's a wake-up lag. The sensors need to first harvest energy from the signals, which is going to add some random delay that is going to prevent you from being able to localize. The bigger problem is that this wake-up lag is completely random. It depends on how far the sensor is, how strong the signal is, and how the environment looks like. And there are so many other factors. And because of this randomness, it makes it extremely hard to compensate for this lag. So our key idea is inspired by our group's previous work is to use backscatter sensor for localization. And to explain backscatter, the way it works is that you have a transmitter and a receiver. A transmitter sends a signal on the downlink, and then the backscatter sensor can then harvest energy from the signal, wake up, and then start responding back to the receiver by modulating the reflected signal. Now, let's go back to the downlink signal. The signal will be reflected back from the backscatter sensor regardless of whether it's charged or not. The signal is not going to wait for the sensor to power up and then to reflect back. It's going to reflect back right away. And when the backscatter node gets charged, what it will do is that it will just start modulating the reflected signal. So then how can we measure time of arrival when we do have continuous reflection in backscatter? And the answer is phase. which is well studied in the wireless localization community. The phase is equal to 2 pi multiplied by the distance divided by the wavelength. So if we can measure the phase, then we would be able to extract the distance and use it to get the location. Now, while all of this is very exciting, there are still some open problems. For example, how do we extend this technique to tracking or even navigation or even robotic manipulation for grasping? And we're really excited to build on the system to enable all of these applications. So, and because we believe in the potential and the challenges, we want you to join us on our journey. And we have already released our code and schematics and step-by-step tutorial for how you can build these sensors from scratch. Also, in the past, we ran a large NSF-sponsored virtual conference called Smart Oceans to bring together oceanographers and computer scientists on a common platform to think about the future of ocean IoT technology. The conference was so successful that NSF might start a new program focused on ocean IoT with up to $80 million of investment. In this area, with up to $80 million of investment in this area, bringing together computer scientists and oceanography to accelerate this field forward. And with this, I want to thank you very much for listening to this talk. Today, I had the pleasure of telling you about our work and vision for a battery-free underwater GPS. I'm very excited about this work, and I look forward to joining you. I'm very excited about this work, and I look forward to you joining us on our mission as we try to explore ocean worlds, understand climate, and support food security. Thank you.